Today I wanted to talk about section 7.1 and angles as we begin the semester. The example we did in class today was given a Ferris wheel, and suppose you start down here at the start position, and you rotate around until you end up at the final position. And so the question is, how much did the wheel rotate? And there are at least three ways we can talk about the size of a rotation or the angle of a rotation. And so one is degrees, and one is radians, and one is revolutions. So if we had gone all the way up to the top, that would be halfway around the circle, a half a revolution. And one full revolution is 360 degrees, so half of that is 180 degrees. Also, one full revolution is 2 pi radians. That's the other measure. 2 pi is about 6.28, and so half a revolution would be pi radians. So we're going to talk about radians and degrees more in a little bit. But you can kind of estimate this angle from here to here is less than 180, so maybe it's about 150. Or maybe you could say it looks like it's about a third of a revolution. And if it's a third of a revolution, it's about 2/3 pi, or 2 pi over 3 radians. And so these are just estimates, but we can describe the distance of revolution in any of those three ways. You could also keep in mind it could be 4/3 of a revolution. You could have gone around the Ferris wheel a full revolution and then up kind of towards the top. So it could be 150 plus 360, which would be 510 degrees. So there's lots of situations where you could talk about how big the angle was, what the rotation was. Another example we talked about was maybe you've got a record player and it's rotating, and you're an ant sitting on the edge of the record, and if the record is rotating at 45 rotations per minute, how fast are you actually traveling in terms of distance? And so there are two ways to think about this. There's rotations or angular velocities, is talking about 45 revolutions per minute, or maybe it's 30 degrees per second, or maybe it's a radian per hour, or something like that. That could be an angular velocity. Another way to describe your speed is your linear velocity, which would be a distance per time. And so for this ant, we've got what's the distance around the record on one revolution? Well, that's the circumference, and that's 2 pi times the radius, which ends up being 37.12 inches. And so your angular velocity is 45 revolutions per minute. You can change that into a distance per minute by setting up this proportion, or this ratio, so that the revolutions cancel out and you're left with inches per minute. And so you multiply 45 times 37.12 and you get that it's about 1,670 inches per minute. You could eventually change that to miles per hour if you wanted to, but we're not going to do that now. A third example is the irrigation problem, where the irrigation system on this farm sprays out in an arc a distance of 400 meters, and so it fills in what's called a sector of a circle, a slice of the circle. And so if you're supposed to have the area of that slice be 150,000 square meters, what's the angle? Well, one way to look at it is, what's the area of the entire circle? Well, area is pi r squared, so the area of the entire circle is that. And so what fraction of the circle do you actually want to irrigate? Well, the area of the sector over the area of the whole circle ends up being 0.298, about 30% of the whole circle. So you want to go about 30% of the whole circle in degrees. That's 107 degrees. So every angle has an initial side, and rotate counterclockwise, we get to a terminal side. Our standard angle will be placed on a set of axes and have going towards the right, 0 degrees, 90 degrees, 180, 270. And there are the three ways to measure the angles. One revolution is 2 pi radians is 360 degrees. It's 2 pi radians because on a circle with radius 1, 1 radian, or the distance around, is 2 pi. And so one revolution we will just say is 2 pi radians. And so 1 radian is the length of the arc. And so then you can do these parts of a revolution. Half a revolution is half of 2 pi, which is just pi radians, half of 360, which is 180. And it turns out if you want to simplify and solve for 1 radian, that's 180 over pi, or 360 over 2 pi, which is about 57 degrees. So 1 radian is about 57 degrees, is a nice conversion factor if you want to know that. So then you can think about all these other fractions of a rotation and try and figure out the angles in degrees or radians for those. And so I've done a few here. The blue lines divide the circle up into sixths, or into eighths, so that the blue lines here are 1/8 of a rotation is each cycle, or each turn, and each one is 360 over 8, which is 45 degrees, or 2 pi over 8, which is pi over 4. And that turns out to be 0.78 as just a number if we want to. But each of these degrees, then we have 45, then 2 of those cycles is twice 45 is 90, 3 is 135, so that's 3 pi over 4. 4 of these slices is 180, 5 is 225, so that's 5 pi over 4. 6 is down at the bottom. Here is 7 pi over 4, and back to 8 pi over 4, which is, again, 2 pi, 1 full cycle. So we'll do those angles more and more. Here they are for a 1/12 of a rotation, which is 30 degrees, or pi over 6 radians. It's too many numbers for me to try and say now, but all those you can practice and get used to. Quickly converting between radians and degrees. Here's the formula that they have in the book. Theta is theta radian, or the angle in degrees. The theta r is the angle in radians. But what I like to think about, rather than that formula, is this conversion, like I've got here. 135 degrees, you multiply by some conversion factor, 2 pi over 360, or pi over 180, and your degrees and degrees cancel, and you end up with some decimal, but it's in radians. Or if you want to go from radians into degrees, then you multiply by 180 over pi, so that the radians and the radians cancel out. And then, in this case, 2 pi over 3 and the 180 over pi, the pi's cancel out, and it comes out to a nice 120. Sometimes it comes out to a decimal, sometimes it comes out to a nice value. But you can do those multiplications to convert. Just keep in mind what the units are, and that'll tell you whether you need to use pi over 180 or 180 over pi as your conversion factor. Another thing that we wanted to talk about is the idea of coterminal angles and reference angles. And we'll come back to these many times throughout the semester. Coterminal angles are angles that end up pointing in the same direction. So, like 140 degrees, this angle over here is the final direction, but I could have done a full revolution and 140 degrees. So if I'd done one spin and 140 degrees, that's 500 degrees. I end up pointing in the same direction. So those are called coterminal. They end in the same place. And so there are infinitely many of these. You could rotate 5 times around and then that 140 and end up at some degree. Or you could go backwards. Maybe it's 140 minus 360. Minus 360 gives you some value. And then a reference angle is a thing that we'll use a lot, where if we've got this 140, that's the angle 140 that we had here. The reference angle, you kind of get 4 similar angles that are all related, these red ones, and they're 40 degrees up and down from the x-axis. And so those 4 angles are going to be related. and the one in the first quadrant is the reference angle. And that's 40, because 140 plus another 40 gets you to 180 degrees. So when we'll talk about reference angles, any angle has 4 related angles in the 4 quadrants, and the one in the first quadrant is what's called the reference angle. Last thing I want to do is arc length and area. So there's a formula for the arc length of the length of an arc, and it's whatever the angle is in radians, so the radius of the circle times the angle in radians. And so there's that formula, S equals R times theta. And if our angle is actually given in radians, it's a straightforward half a radian, and the radius is 4, you get 2 feet. But if your angle is 2 pi, then this theta becomes 2 pi, and you just get 2 pi times the radius. So if your angle is the full revolution, a full 2 pi, your arc length formula becomes the circumference formula, 2 pi r. And so this is really just saying I go a fraction of the way around the circle, I get a fraction of the circumference. I go a third of the way around the circle, I get a third of the circumference. I go 17% of the way around the circle, I get 17% of the circumference, and that formula works. The same idea works for area. If I take what fraction of the circle am I sweeping out, like with this area, I get theta over 2 pi, so that's theta over the entire circle, times the area of the entire circle. And if you simplify that, you get 1/2 theta r squared, if you're in radians. If you're in degrees, then it's the same idea. Theta is 360, and that comes out to be, this is if you do a full circle, it's 360. If you're in degrees, the area is theta over 360 times pi r squared. So that theta over 360 is just your fraction of a circle times the area of the whole circle. And so in the book they talk about a couple different formulas depending on if you're in degrees or in radians. They're both the same if you think about it as a fraction of a circle times the area of the whole circle. And so let's go back to our irrigation problem. We had this irrigation problem where the radius was 400 meters, and here's the formula for area. We wanted to know what angle do we need so that the area is 150,000 meters, or square meters. And so we can just do that and solve, and we end up dividing by 400 squared, which is 1600, and you get 1.87 radians, 1.875 radians, and it turns out if you change that to degrees, that's the same 107 degrees we had way back before. So these are some of the examples I wanted to talk about with degrees, radians, and rotations or revolutions, arc length, area of a sector, linear speed, and angular speed. So let me know if there are any questions you have about these.